This is the video for 1.2, analyzing graphs of functions and relations. So first we're going to look at graphically representing functions. So if we look at this function that we have right here, okay, I want to do the domain and the range, x-intercepts, y-intercepts. Now one thing you'll notice with the domain is, normally if this was a continuous graph, it would be all reals, negative infinity to positive infinity. However, there is a hole in my graph, so I'm going to have to exclude this x value of -2 in my domain. So my domain is going to be negative infinity, oh, hold on, negative infinity to -2. I have to skip over -2. That's a really bad infinity. And go out to infinity. My range, if you look, is going to be everything including, even though there's no value here, there's a value over here on the right. So my range is going to be all reals. Then for my x-intercepts are going to be here, here, and here. And when you write intercepts, you need to write them as coordinates. So I've got -3, 0, -1, 0, and 3, 0. And my y-intercept is going to be right here at 0, -7. Let me move this up. Okay. Next, we're going to algebraically represent functions. So if I want to find an x-intercept, I need to set my y value equal to 0 and solve for my x. And make sure that you write your answer as a coordinate. For a y-intercept, I'm going to set my x value equal to 0, solve for y, and write it as a coordinate. And make sure to note that if you do not write intercepts as coordinates, regardless of what the book says, I will mark them wrong. They need to be written as coordinates. Okay, let's look at these two examples here. So first off, I have -2x cubed plus 4 over 3. So to find your x-intercepts, you're going to set your y equal to 0. And in this case, remember your f of x is equal to your y. And when you're dealing with rational functions here, the only way to get a 0 out of a fraction is to have 0 over anything. So this denominator is not going to matter. So all you really care about when it's a rational function is setting your numerator equal to 0 and solving. So you get -2x cubed equals -4. If I divide both sides by -2, I'm going to get x cubed equals 2. And then you need to take a cube root, and you get your x-intercept as cube root of 2. Make sure that you write it as a coordinate, or I'm going to mark it wrong. For my y-intercepts, I'm going to set my x equal to 0 and solve. So this whole entire thing here is going to become 0. So 0 plus 4 over 3 gives me 4/3, and as a coordinate that's 0, 4/3. We're going over these now because you're going to need to find x and y intercepts at various times. We're going to do rational functions in chapter 2. We're also going to be factoring a lot. We're going to be graphing polynomials in chapter 2, so you need to be able to graph them, or find x and y intercepts in order to graph them. Okay, next one. Now for this problem right here, this is a higher degree polynomial. So you can try and factor it, but it's not going to be factorable. So for this, you're going to have to go back and remember a little bit from Algebra 2. And if you remember from Algebra 2, we did synthetic and long division. So in order to do synthetic division, I'm going to try all of the numbers that are factors of 4, which is plus or minus 1, 2, 3, and 4. And that's all over the factors of 1, which I don't have, or which is just 1. So you're only going to need to try 1, 2, 3, and 4. So you just have to get one of them. If I can find one of them and get it down to quadratic, I can factor the rest. And since this is 4 and it's not very big, I'm going to start with something small. I'm going to start with 1. And then, if you remember for synthetic division, you need to take all the coefficients of your polynomial, including any that are missing, and then you do synthetic division. So you bring down your first number, you multiply these two together, so 1 times 1 is 1, and then you add them. 1 times 2 is 2. Add them. 1 times negative 4 is negative 4. And as long as you get 0, that means you've reduced it down to a quadratic that you can either factor or do quadratic formula on. And since I'm going to have to do quadratic formula, I'm going to have to move this up. So remember quadratic formula, this is a, b, c. So it's x equals negative b plus or minus the square root of b squared minus 4ac, oops, that's a negative, all over 2a, oops, 2a. So that's going to give me x equals negative 2 plus or minus the square root of 4. This all gives me plus 16 over 2, which is negative 2 plus or minus square root of 20 over 2. You need to simplify your radical, which simplifies to a perfect square of 4 times 5, and then your square root of 4 is 2. So this ends up being negative 2 plus or minus 2 root 5 over 2. You divide everything by 1 and you end up with negative 1 plus or minus square root of 5. And since they are coordinates, you're going to have this 1 up here is one of your x-intercepts, and these are your other two. So my x-intercepts are going to be 1, 0, because that was the one that you got from up here that you did originally. And as long as it went in and you gave your remainder of 0, that's one of your intercepts. Negative 1 plus square root of 5, comma 0. Negative 1 minus square root of 5, comma 0. You have 3 x-intercepts. Now for my y-intercepts, you might have to pause this right now if you need to still write, because I'm going to have to pull this down. So take a minute and write down what you need or pause it. And now we're going to pull the screen back down. So for my y-intercepts, to find a y-intercept, let's use a different color. My y-intercept, I'm going to plug in 0 for all my x's. And really, all that's going to be left is the 4. These are all going to go away. So you have a y of 4. So your y-intercept ends up being 0, 4. Okay. Next, we're going to look at symmetry. There are 3 kinds of symmetry. This is probably review from Algebra 2. So we're going to go through this fairly quickly. X-axis symmetry basically means, oops, let me draw pictures. Means that your graph is going to hug your x-axis. Y-axis symmetry means it hugs your y-axis. Origin basically means you can rotate this 180 degrees about the origin. And so this hugs, the y-axis hugs your y-axis. X-axis symmetry hugs your x-axis. Then let's look at it algebraically. So algebraically, you're going to replace your y, not your x, with negative y, and if it gives you your original equation, and I should say not if, and it gives you your original equation, that's how you know you have x-axis symmetry. So for y-axis, we're going to do the opposite. We're going to replace x with negative x. And if it gives you the original equation, that's how you know you have y-axis symmetry algebraically. Move this up a little. For origin, you're going to replace both. You're going to replace y and x with negative y and negative x. And if it gives you your original equation, and it gives you your original equation. That's how you know that it has x-axis symmetry. So even, odd, or neither, I'm going to do on the next screen, but because I can't go back to it, I'm just going to tell you now, and I'm going to refer back to this. X-axis symmetry, if you look at, for example, let's start with y-axis symmetry. If I look at this one, just so that you have an idea of it, what does this remind you of? I use this as an example. This reminds you of a quadratic. So that is considered even. If I look at origin, what does this function remind you of? This reminds you of a quadratic, or I could have even done the same thing and drawn in a line here. So if I have x or x cubed, that is going to be your odd. When you have an x-axis symmetry, it's not going to be even or odd. This is going to be a neither. So when you think even, you need to think of like an x squared, x to the fourth, what those would look like. For an odd, you're going to think an x cubed, an x to the fifth, whatever those look like. They all will have the same basic property, and we're going to look at that on the next screen. Okay, so let's pull this up. I want to see what type of symmetry x minus y squared equals 1 has. So if you don't know what that looks like, you probably can figure it out, but it's got a y squared, so it's probably not going to be a function. But if I'm checking mathematically, if I want to check for x-axis symmetry, I'm going to plug in y in the, or negative y in for y squared equals 1, and simplify it. So that gives me x minus y squared equals 1. And if it stays exactly the same, which it did, it has x-axis symmetry. If I want to try y-axis symmetry, I'm going to replace x with negative x, leave the y alone, and check to see if it gives me the exact same equation that it did originally. So no, it does not have y-axis symmetry. Then I'm going to check origin symmetry. And just because you have one or the other, or you don't have an x or y, you still could have origin. I'm going to plug in a negative x for x, a negative y for y, and check. So that gives me negative x minus y squared equals 1. So that's not the same. So the only one that it has is x-axis symmetry. Sometimes you can have origin but not have x and y. Okay, then we're going to talk about even or odd. We talked about it a little bit on the last screen, but we're going to talk about that again. So evens, in your head, you need to think like x squared, x to the fourth, anything like that. Absolute value is also even. A constant is also even. Odd are going to be things like x, x cubed, x to the fifth, anything like that. So for an even function graphically, it's going to look symmetric to the y-axis. So it's going to have y-axis symmetry. And for odd, it could be a line. It could be something that looks like a cubic. It's going to have origin symmetry. Okay. If I want to, let's say I give you a function that you don't have any idea what it looks like, because an x squared, an absolute value, an x cubed, you probably already know how to do all of these. But if I give you, let's say, for example, a trig function that you've never seen, you need to be able to figure out algebraically. So if it's even, when you plug in negative x for x, if it stays the same as the original, then it's even. So when you substitute negative x for x, and the function stays the same, then it's even. If you plug in negative x for x and the whole function changes signs, then, so when you substitute negative x for x and all your signs change, then it's odd, meaning you go from positive to negative, negative to positive, then you know that it's going to be odd. Oops, I'm trying to move this up. Okay, let's move this up. Okay, so first we're going to mathematically look at how to calculate whether functions are even or odd, and then I will give you a shortcut. So if I want to find if the following functions are even or odd, I'm going to substitute in negative x for x and see when I simplify if I get the original. So this gives me negative x cubed plus 2x. And if I check, I went from a positive x cubed to a negative x cubed, a negative 2x to a positive 2x. So since all of my signs changed, that means this is odd. Second one, I'm going to plug in negative x. Okay, so when I substitute in negative x, are you going to be able to simplify negative x? If you remember from Algebra 2, really it's going to simplify to 4i root x. However, that means that this is not exactly the same as this, and it's not like the signs change. It didn't suddenly become a negative 4 square root of x. It's a 4i square root of x. So this is a neither for that one. And then on my last one, if I plug in a negative x for x, negative x to the fourth plus 2, that gives me x to the fourth plus 2. These two stayed exactly the same. Since these two stayed exactly the same, this is an even function. Okay, that's mathematically how you find it. So if I ask you to mathematically determine whether it's a function or not, this is what you need to do. However, there's a shortcut. You can also look at the even-odd properties of each individual term. And if you remember from way back in Algebra 1, this is a term, this is a term. Terms are separated by addition or subtraction. So there's 4 terms in the second example. There's 3 terms in the last example. So if you look at each individual term and figure out what kind of function it is, then you can look at the problem as a whole. So if I start with x squared is an even function. Okay. If I look at a constant, okay, think of this as 2 to the x to the 0 power. Okay. And so in this case, we consider the 0 as an even function, or think of this in your head. If I told you to graph y equals 2 and you graphed it, that would be a horizontal line. And horizontal lines are going to be symmetric to your y-axis. So this is also going to be even. So if each term is the same type of function, whether even or odd, then that means the whole thing is even. So even if you don't know what the graph looks like, especially when we start getting into these funky ones here, or we start getting into like higher degree polynomials, and you're not sure what it looks like, you can figured out by each individual term. So let's look at the next example. So my x cubed is odd. And then absolute value of x is a V shape. And it's symmetric to the y-axis. So this is even. If I look at x squared, that's even. And x, remember, means x to the first power, so this is odd. So when you mix odd and even functions, this is going to be a neither. It's neither even nor odd. Okay. Then the last one, I have square root. So when I look at square root, your square root looks like this. That's what a square root graph looks like. And that is neither. It's not even or odd. If I look at 2x, that's odd. And if I look at 3, that's the same thing like having 3x is 0. That's even. And so since you do not have the same thing on all of them, that is a neither. So that is the end of your 1.2 video. Okay, go on to the next one.